So good morning, everybody. My name is Cormac Toher. I'm an assistant research professor at Duke University in the Center for Autonomous Materials Design. So we're going to be presenting this morning. So for the next 3 hours, we're going to be talking about AFLOW, which is our integrated infrastructure for computational materials discovery. So the other people who are presenting today, so we've got Dr. Corey Osis, Dr. David Hicks, and Dr. Marco Westers, who are all postdoctoral researchers in our center. And Professor Stefano Controllo is the director of our center. Okay, so I'm going to give a quick introduction overview to AFLOW. And then so Corey, David, and Marco then will be teaching individual sessions about specific parts. So just to give some brief logistical information. So as Ichiro mentioned, there's going to be 2 breakout rooms. We'll use one for technical support and either for AFLOW support. So the technical support room is for issues with things like Zoom or Colab, while the AFLOW support room is for specifically about questions about AFLOW and tutorial content. So if you do have a question or a problem, please send a message to us in the chat, either to the host or to everyone, and we will assign you to the appropriate breakout room. Also, one thing we would like to mention is that when we were testing, we had some issues with Google Chrome for Colab, especially with displaying images. So we suggest using Firefox or Microsoft Edge, which seem to work better, at least in our experience, for the exercise we're trying today. So if you are having some problems, you might need to switch browser. Okay, so just some introduction as to why we're actually doing this sort of automated computational materials design. Well, mostly we're motivated by novel materials applications. Some examples here. For example, one of the big things we're working on at the moment is thermal barrier coatings. So if you want to put a barrier coating on top of a turbine blade to protect it from the effects of, say, the combustion products, or from the high temperatures of the combustion process, you put a sort of a barrier on top that's both corrosion resistant and also will have a high melting temperature, and we'll be able to protect the underlying turbine blade. Some other examples will be, we're looking for super hard materials for things like machine tools, so for cutting tools, for coatings on top of things, these sort of things, wear resistant coatings. We also have been looking for things like biocompatible corrosion resistant alloys for medical implants, photovoltaic materials for solar energy harvesting, solid state electrolytes for things like lithium-ion batteries. We've also done some work looking for superconductors, or for example, for another application that you can use our data for will be things like heat sinks for advanced electronics. Okay, so to try and give you an idea of the scope of this material space, first, if we look at the periodic table and we look at all the materials that have stable isotopes, which are non-noble gases, so the ones that actually we usually use to make materials, we have about 78 of these elements. To combine ways we can combine 2 of these elements, we can combine these about 3,000 ways. When you go up to ternary compounds, you get to 76,000. By the time you get to quaternaries, you're over 1 million. For 5 components, you're 20 million. And by the time you get to 6 components, you're already at 250 million, just different combinations. Then if you also add in the fact the thing that you can have different polymorphs, so different underlying structural prototypes, which David's going to talk about in the next lecture. If you can also have different stoichiometric ratios, we find that you get to something of the order of 10 to the power of 177 different possible hypothetical materials that you could create. So if we want to actually identify which ones will actually form, which ones will have useful properties, you can't really do this individually. So you need to start automating the process. So to do this, we do what we call automated computational materials discovery. So our workflow looks something like this. We start from either already experimentally observed materials or what we call structural prototypes, which again, David is going to talk about shortly. We then decorate these structural prototypes with different combinations of elements. Then we perform automated density functional theory calculations. So we use this, what we call this FAST code. Yeah, then we pipe the results into a searchable, sortable database, which is available at aflow.org, and which we're going to talk about in it. But I'll introduce it briefly, and then Marco will talk in a bit more detail about how to actually extract data. And once that's done, you can interrogate it to find candidate materials for specific applications. You can also use the data to train machine learning models to sort of accelerate this discovery process. And at the end, in the final session, Corey's going to talk a little bit about some of the machine learning models that have been trained with AFLOW data and how you can access these models using an online API. Okay, so this is how the AFLOW itself works. So it wraps around the density functional theory code. So from a single AFLOW.in file, you can generate, so this is sort of the input file for AFLOW. You can generate multiple different DFT calculations. It will monitor, while these DFT calculations are running, it will monitor them. If it detects an error, it will automatically edit these AFLOW.in files. So it will append something, new instructions to the end to try and get the calculation to converge correctly. So it might modify some parameters, except calculation parameters, and so on. So it automatically detects the error and it knows what to do for certain errors if it sees them in the output file. Then it can combine multiple sets of DFT calculations to do things like thermal or elastic properties. We can also then use large ensembles of calculations to predict things like the formation of disordered materials, to do statistical thermodynamics, etc. We can also then extract electronic information such as the electronic band gap out of the results of the output data of the DFT code. And then at the end, we format this data and we pipe it into an online database for online storage and dissemination. Okay, so now I'm going to briefly introduce our database. So the web portal is available online at aflow.org. So here you can see the front page. We have now over 3.5 million materials entries and something like 700 million individual properties. Here you can see a breakdown of the individual properties. So for example, the number of band structures, etc. We also have just started a seminar series. So we have both the AFLOW school, so for example, these type of tutorials, and we also have these online seminars that are being held every 2 weeks. So the next one will be next week at 10 a.m. Eastern time. And here's a standard, so you can sign up for these seminars. Once you sign up, you'll basically just enter your name and your institution and your email address. You'll get an email with a Zoom link so you can attend. So if you want to see more information, you can go to aflow.org/seminars. Okay, so if you scroll down on this aflow.org page, you'll see what's called our apps and docs section. So we have various online applications, which we'll be talking about today. So for example, David is going to talk about this crystal prototype section on the AFLOW online, while Corey is going to talk a little bit of AFLOW ML. Also, the AFLOW ML and the database, the search page also have some APIs, so you can do these things, also do these things programmatically, build them into a workflow, and we'll describe how to do that as well. But first, I'm going to introduce what's this search application. So this is something you can do online, just through your browser, if you want to do some simple searches, and we're going to go through how to do that now. So here's if you click on this advanced search page, it brings you to this page, so aflow.org/search. So we have various features. So for example, you can select different elements, different combinations of elements. You can also select groups of elements. So for example, if you want to look for alkali halides, you can select alkali metals and halogens. You can also then specify the number of species. So if you just want alkali halides, you specify the number of species to be 2, and that will give you things like sodium chloride, potassium bromide, and so on. You can also perform logic operations, so you can and, or, not, etc. So we can also bring up property filters. You can either use a slider, so to go from the element selection to property filters, or you can click on this display link and this will bring everything up on one page, depending on your own personal preference. So here's an example where everything is on one page. Here we have the property filters. So here's an example. Here I've selected the elements sodium and chlorine. So we're looking for sodium chloride. Here I've selected the electronic properties. So I want to see the electronic band gap. And so it automatically also gives you back the space group and the Pearson symbol, so you have some structural information about the material. So then I've also set the number of species to 2. So I only want sodium and chlorine. And then to add different filters, you click on these and then you click the add button here. And then if you can also restrict the value by clicking on this button here, and then you can specify a range in this results section here. So before I go to the actual a brief exercise, I'm going to go through this using the online page just to give you a demonstration of what you would actually do in practice. Okay, so.
Cormac, I got a request to ask
Yeah.
if you could speak a little slower.
Oh,
That's
okay,
possible.
sorry. Well, okay, I'm going to go through the search page now, so I'll probably go through this somewhat slower. Okay, so like I said, we go to the.
Also,
so,
Cormac, I'm sorry to interrupt, but we have these polls that you can launch.
oh yeah, so maybe check that everything is following. We can do that.
Yeah, so like once in a while, like, yeah, stop. And
What I'll do is after this, after I show the online thing, I'll do the poll. Okay, so here we have, if we go to the AFLOW site, and there's also, just for your information, if you're having problems with the aflow.org page, there's also a mirror site here, aflowlib.duke.edu/search/UI.
maybe can you make it a little bit bigger too?
Yeah. Okay, I don't think I can make the page itself
Bigger than that? Okay, that's fine.
This. Okay, so if we scroll down, we get our Mendelib search option. So here we have our search page. So then we want to click on, let's say we want to look for alkali halides. We click on alkali metals and halogens. And then we would number of species is 2. Then we want to, if we want to do the property filters, then we scroll down. We want to add an electronic band gap. And then we can click here to restrict value. And then we can give, let's say we want something between 2 and let's say 5 electron volts. I don't know if there's anything in that range, but let's see. Then we hit search. And here you can see the things that come back. And most of these, so you've got cesium bromide, potassium bromide, and so on. And we get a total number of results here. So here it says how many results it returns. So here it finds 161 entries. The other thing you'll see here is that it creates this, what's called this AFLOW summons. So this is something that Marco will talk about in a later part of this workshop. So, but this is, you can use this also to access this data programmatically. So you can return, for example, a JSON file that you can then use, do some processing on, use as input to machine learning algorithms, for example, or other types of workflows. So JSON files tend to work quite well with the Python language. Okay, so let me run a poll, and then we'll go and we'll try an exercise so people can try this out and find an example. Polling. Okay, so it looks like most people seem to be following along. So let me just bring it back up to PowerPoint. And then we'll go, and now we're going to do some quick exercises. So I'm going to give you a few minutes to work on these.
There are 2 questions in the chat for you.
Okay, let me just check these. Okay, how do I get?
There it is, 3.
Okay, can you put AFLOW in context relative to some other databases in terms of its goals and capabilities? Okay, so historically, AFLOW was focused more on metals. So we're probably the database that has the most metals, most metal calculations. We also are the database, the computational first principles database with the most actual materials entries, as far as to the best of our knowledge, at least that are generated in the same way. There are other databases that are aggregate databases, such as Nomad, that have more entries. But if you look at their actual breakdown, you'll see that something like half of their entries are actually from AFLOW itself. So somebody then is asking about X-ray diffraction patterns. We have the code to do this. It's not something we've added to the database yet. It's something that it's something that we're working on. It's on our to-do list, but we haven't actually put it online yet. There's still some work that's needed to do to interface it, to make sure the output is correct and all this kind of things. So how do I get to the AFLOW library? So, okay, so the AFLOW library itself, like I said, if you just go to your browser and you go to aflow.org, or you can go to, let's see. If you go to aflowlib.duke.edu/search/UI, this will also bring up the search page. Can you post the link? Okay. So there's two different links you can use. You have aflow.org and aflowlib.duke.edu/search/UI. And so the answer to if we're, okay, so are you continually searching DFT simulations to increase the results in the database? Yes. So we're always running the calculations. So we usually, not sure what rate we were adding at, but we, like, to put it this way, I'm continuously having to update these slides to get the right numbers for the current database. So we usually add maybe about 500,000 entries a year, I'm going to say, as a guess. That's sort of the order of the rate at which we run calculations. Speaking of metals, can you search based on percent weight? So percent weight is not something we've added yet. It's actually an interesting thing to try and add. Really, we're using, okay, because we're doing from first principles, we don't so much count the mass of what we have inside as we do the number of atoms of each species. So you'll be looking by molar percentage rather than by percent weight. And within molar percentage, you'd be essentially searching by the stoichiometry. I'm not sure how well we can search by that. Maybe Marco can try to show you later. I'm not sure if the search for that that's not a straightforward thing to search by, but it is information we do have in the database. If you're looking for convex whole phase diagrams, it's not something we're going to go through today, but you can also again look essentially by composition. Okay, so here's the results. It looks like 80% of the people seem to be following fairly well. And let's ship the results. Okay. Okay. Okay, so now we're going to try a couple of quick exercises. So these are just simple ones where you can use the online database. Again, if you have problems with the aflow.org website, you can also go to this aflow.duke.edu/search/UI that I've shown here in the chat. Okay, so the two exercises. The first one is to try and use the advanced search functionality on the AFLOW website to find the band gap for silicon carbide in the zinc blende structure. So this is space group number 216. The other one is to use the advanced search functionality to find materials containing tin, but not lead, with band gaps between 1 and 3 electron volts in the ICSD catalog of the AFLOW database. So for the ICSD catalog, you don't really have to do anything. This is already set by default on the search page. And then check how many results are returned. So I think it's now 9:28. So let's take 5 minutes to do this. And then I'll go through and I'll show you how to actually, I'll briefly go through and I'll show you how to do it. So if anybody has any questions, you can also ask in the chat now. Okay, so somebody's asking why are there 10 entries for silicon carbide? So somebody's obviously already been able to do the first exercise. So these are based on the ICSD, so this inorganic crystal structure database. And within this ICSD, there's actually quite a lot of duplicates, especially for common materials. So this is where, so we find that a lot of the time, this is basically people have measured the crystal structures at different temperatures. So they might be trying to look at, let's say, the lattice constant as a function of temperature. So they report all of these different crystal structures, so at each different temperature or maybe at different pressures. So there's actually quite a lot of duplicate materials inside the ICSD. So we run them as separate ICSD entries. They all relax the same structure. And then one of the things that we do is to try and identify which ones of these are duplicates. And this is something that David is going to be talking about next when he's talking about Excel Finder. And that's like a major part of what AFLOW does, is to try and identify which structures are actually structurally identical, which ones map onto each other, as well as looking for materials that are identical, also looking for what underlying structures are identical. And this is to try and identify what we call structural prototypes that most of our database is actually built off of. And you actually have to be a bit careful with the ICSD, because one of the things we find is that, in fact, we've noticed is that they do tend to remove entries over time. So if they themselves see that an ICSD entry is a duplicate, they will actually remove it from the next addition to the database of the database. So sometimes you have to be a bit careful about citing an ICSD number in a paper, because there's no guarantee that that ICSD number will remain valid over time. So that's something that we do actually want to warn people about, that we've actually noticed. Okay. Okay, so here's actually a very interesting question. Does the database include glass compositions and amorphous materials as well? Okay, that's actually a very interesting question, because we actually do quite a lot of work on metallic glasses. Now, the database itself only contains ordered crystal structures. So everything within our database is based on what we call these crystal prototypes that David will talk about in a bit more detail next. But what we have done is looked for trying to estimate glass forming ability based not on trying to calculate the amorphous structure, but rather on doing ensembles of ordered structures. And then we look at our idea is that we have a lot of these ordered structures that are similar to each other in energy, but different from each other structurally, then the idea is that they compete against each other and will frustrate the crystallization process. Then the next question is, what do you have for lib? I'm not quite sure what you mean by lib, LIB. Oh, so you mean on the database itself? Oh, lithium-ion batteries. Okay. So for lithium-ion batteries, this is not something we have worked on much in our group so far. We do contain like lithium compounds. So 2D materials. Okay, another question. So we do have a few 2D materials, the ones that are reported in the ICSD, but this is not something we focus on ourselves, research-wise. We're more we tend to be, historically, at least, AFLOW tend to be quite focused more on structural materials, so metal alloys, metallic glasses, these sort of things. And currently, we're looking a lot at disordered materials. Okay, so he's asking, so this is another question. If the entries are not actually duplicates, but are different measurements, how do you decide on the entry to be kept in the database? So from our point of view, we keep everything. We don't delete an entry in the database from our database. Now, what we do try to do is that when we have ones that are duplicates, we will, if we're running additional workflows on top of this, for example, if we want to calculate something like elastic constants, then we're not going to do this for every single one of these duplicates. So we do select one, and that's usually the one that's whichever is the lowest ICSD number, or based on like maybe some other details on checking how well the calculation was converged, etc. So there's some details on our end. Now for the ICSD, I'm not sure what rules they use internally. I think they use whichever one was reported first. So yes, so the next question is about using silicon carbide, you get 44 entries, but using all AFLOW, we get 333. So yes, the entries, all AFLOW contains ICSD plus the hypothetical structures. Yes, that's everything. So the hypothetical structures is much, much larger than the ICSD part. The ICSD part is maybe at 60,000 entries, while the rest is well over 3 million. Okay, so it's now been more than 5 minutes. So let me go through the actual exercise. Let me just bring it up. So the first one is find the band gap for silicon carbide with the zinc blend structure. So here we do silicon, carbon, number of species is 2. We want the electronic band gap. We don't have a specific value, we just want to find out what it is. But we do want to restrict the value for the space group. So we go from 216, 216. So I hit search. And here we have 10 entries for this specific space group. And we get an electron band gap of 1.37 electron volts. Now the next one we wanted to do is now if we do that for all AFLOW, instead, let's see how many entries we get. It might take a little bit longer. Okay, we still get the same because for this particular material, we haven't really done this for the all AFLOW because silicon carbide is not really a material we're working on. But let's do now the lead and tin. So we want ones that contain tin, but not lead. And then we don't want to restrict the number of species. But we do want, and we don't want to restrict the structure, but we do want to restrict the electronic band gap. In this case, was between 1 and 3 electron volts. So again, we can search. So maybe a bit more about the while this is running, a bit more about the difference between the ICSD versus the rest of AFLOW. So within the ICSD, these are materials that have already been reported. So tend to be more interested in calculating additional properties. So things like elastic properties, thermal properties, electronic properties, and so on. So you'll generally find more data for these individual materials. For the rest of AFLOW, these are hypothetical materials, and our priority is more on materials thermodynamics. So identifying which one will actually form. So for modeling alloys, this is really where the rest of AFLOW comes in. So we're not in that, we're basically doing what we call these structural prototypes, where we have we're looking at, again, all the possible different structures that could occur locally within the alloy. So we generate this for the entire alloy system. We then use this data to generate statistical ensembles. So then we can predict things like solid solutions, which are more like what would actually occur in alloys. So this data isn't really available online yet, but we do have a paper. Maybe Corey can add it in the chat as well. So that the LTVC paper, I don't know if you have the link for that, Corey. But yeah, so this is a paper we did on predicting of the order, disorder, transition temperatures.
Yep, 1 second.
Yeah.
1 second.
Energy above hull. Yes, so this is the convex hull application. So I'll show it here. So it's not something we're going to go into detail today on, but it's this application here on the front of the database. You can also use this directly through AFLOW itself. So you can look inside, and again, you have a thing where you can select your alloy system, submit, and that will generate a convex hull. Okay, so let me go back to the search page. So here we found, after we run this, we found 389 entries that satisfy our search query. Oh, sorry, this one I'm searching all of AFLOW, but if I do ICSD only and run it again, you should say 369. Yeah, 369 entries. Corey, if you want to add the convex hull paper in there as well. Oh, you have.
Yeah, I threw it in there already.
Okay, yeah. Okay, so let's go back to the slides. I'll keep this thing on time. Okay. So just to mention, we also the underlying code is also available. So the code is used to generate all the data. It can be used on Linux, Mac, and Windows. So it's available under the GNU license. You can also use it on Windows, but you need additional software. So you need either a Windows subsystem for Linux, so for Windows 10, or Cygwin for the Windows versions. And you can get the instructions and installation scripts from here from aflow.org/install-aflow. Okay. Once you install, you'll get this what's called this .aflow.rc file. So this is a hidden file, so it's something you have to look for carefully. But you can then set different things like the path for the VASP executable, different settings for the VASP, so where your pseudo-potential files are, as well as AFLOW settings like output file names, graphic settings, and so on. And all this will be covered if you look online, but we're not going to go through this in today's class in detail. So we just want to mention as well that we have some information on past and future AFLOW schools at aflow.org, aflow-school. So the various length from the half-day tutorial to a full-day workshop through the multi-day school, like the one we mentioned earlier that we ran 2 weeks ago in Texas, at Texas A&M. And if you go to aflow-school, you'll also see some, you can get videos of previous tutorials we've run. So if you want more detail on how to use AFLOW, for example, you can go there. And if you're interested in hosting one of these workshops, you can also contact Professor Cardarolo at stefano@duke.edu. Okay, so then just to pass over what we're going to be doing for the rest of this section is, so next, David Hicks is going to talk about AFLOW Sim, the AFLOW prototypes, and the Excel Finder. Marco Esters will give a brief overview of the database and then talk more about the database interfaces. So we talk about the AFLOW Search API. And then finally, Corey will talk about the AFLOW ML API, which you can use to, again, programmatically access these machine learning models that have been trained on AFLOW data. So with that, I'm just going to pass it over to David.